Let's get on with, we were talking last time about volumes of revolution, and the idea is you have some kind of a three-dimensional shape which is obtained by rotating a function like this, say, from A to B. I'm going to try to draw this nicely. If you rotate this shape around the x-axis, the other side of it, I guess, looks something like that. Oh, that looks pretty good. This little sort of Dr. Seuss hat kind of shape. All right. And the whole thing that we are talking about in this section is the volume of this kind of a thing. Of course, not all shapes in the real world can be obtained in this way by revolving something around the x-axis, but many shapes can, and this is how you can find the volume of such a thing. All right, and we just towards the end last time had this formula, which you should memorize, I suppose, although it's not all that complicated. This is the formula. What it comes from is basically pi r squared. The idea is if you were to slice this picture up into a bunch of little bits in the same way that we like slice up the area under the curve into rectangles, since this is a three-dimensional thing, if you do the same sort of slicing, each of the slices looks sort of like a little disc or something, a platter of some sort, right, with some sort of a circular thing with a little bit of thickness. And if you pull that thing out, what you get is really a cylinder, a very short cylinder, and its volume is given by the formula pi r squared times the height. That's why you have this pi, and then this f of x is basically the r squared, because f of x is the vertical distance here, which is the radius of one of those little circle things. So that's where this formula comes from, although you don't have to remember all the business really, as long as you can remember the formula. All right, so this is the formula for, now we're going to do more complicated version of this later on today, but this formula works when revolved around the x-axis. Now we are going to talk about revolving the figure around some other line, which will require a slightly different formula, but this is the formula for when revolved around the x-axis. All right. I don't think we did any examples of this last time, but this is fairly easy to use this formula. I mean, there's not a whole lot to it. You just have to put the pi there and then square the function on the inside. So let's just try a simple one, and then I have some more interesting ones. How about my favorite slightly interesting function is y equals x squared, and let's say, can we find the volume of the region from 0 to 1 when you spin it around the x-axis? So the shape that I'm talking about would be some kind of a little something like this, right? It's like a little bugle or something. All right, a pointy hat, perhaps. I want the volume of that shape. And really, all there is to do is plug it into the formula there, and this is a fairly straightforward example. So here it's just going to say the volume is pi, so you always just have a pi there. And then integral, in this case, I'm going to go 0 to 1, because those are the, that's the range over which I'm taking this volume here. So it is from 0 to 1. That's the range of x values. And then on the inside, I go f of x, the whole thing squared. In this case, f of x is x squared, so it's x squared squared, right? The function I'm talking about is x squared, but there's already a square in the original formula, and so I'd really need sort of those two squareds. And now we just have to do the integral. As usual, I like to simplify inside the integral as much as possible before actually doing it. Anybody recall, how do you do this squared? What does that come out to be? Square inside a square? Yeah, x to the 4. In this case, you should be multiplying those two exponents. And so this is 2 times 2, which is 4. All right, and then we just do the integral. So I get pi and then 1/5 x to the 5. Plug in 0 and 1. You plug in the 1, I get pi times 1/5 times 1 to the 5th, and then minus pi times 1/5 times 0 to the 5th. And of course, that second part there is 0. Really, this is just pi times 1/5, or you could say pi over 5 if you like. So this is a simple example of this kind of volume thing. Yes?
If it's like a quiz, would you want us to simplify it, or could you leave it?
You could leave it like this if you like. Is that what you're saying? Yeah. Either one of these would be fine. I usually wouldn't simplify it, although this is just like zeros and ones, so to me it's not so onerous. All right, great. So that's a weird sort of bugle shape. Let's talk about maybe an example with a more perhaps more interesting shape or something, more like ordinary kind of shape. I don't know if anybody cares about bugle type shapes like that. How about find the volume of a sphere with radius 2. All right. Now this is something that I'm sure you learned at some point in your youth. There's just like a formula for the volume of a sphere, which you could just plug in. But I want to do this kind of by hand without using the formula, and that's really what I kind of like about this. Doing the volumes by integrating, you can actually find this volume without using the sort of memorized formula for the volume of a sphere. But just for the sake of checking our answer, can we just, let's sort of do it that way first. Anybody actually remember the volume of a sphere formula? This is slightly obscure, but I don't really care if anybody remembers it, but this is cute trivia. It is 4/3 pi r cubed. This is the formula for the volume of a sphere. Anyway, if we do it in this particular example, the r is 2, so we should get 4/3 times pi times 2 cubed. 2 cubed is 8. So if I were to simplify this, it would be 4/3 times pi times 8. 4 times 8 is 32. So this, I'm just going to use this to sort of check our answer at the end. It should be 32 over 3 times pi. If we do everything right, that should be the correct answer. All right. So I want to see if we can do this sort of by hand. Now, I didn't even tell you a function or anything. Like eventually we're going to use this formula, of course. This is the volume formula that we're going to use. But we don't know what the f of x is. We don't know what the a and the b are. What you have to ask yourself is sort of, how do I make a sphere by revolving some shape around the x-axis? Any ideas about this? If I want to make a sphere, what should the curve look like that I start with? You have to sort of visualize a little bit. Of course, if you start with, if you start with this, you get this kind of bugly shape. What would I want to start with to actually get a sphere? Yeah?
A semicircle?
A semicircle, he says. Yeah, I like that. If you start with sort of a, maybe I'll just draw like the top half of a circle. Whoa. It was looking so good. Something like that. That's supposed to be a circle, right? And this, if you were to spin it around the x-axis, it does indeed make the sphere that we are looking for. And we can label some things. I said radius 2, which means this goes out to 2, right? And it goes back here to -2. So actually that's going to be the a and the b, right? The range of the x values when we do the integral is going to be -2 to 2. And what is the function? It's that sort of top of a circle. Now we have to write this as a function. Anybody got any ideas about that? There's a standard way to write. It's maybe a little weird because it's only the top half of the circle, but perhaps you remember the way to write the equation of the full circle. Actually, if you took, in this picture, if you took the whole circle, it wouldn't really matter, right? You still get the sphere that we want if you revolve this around the x-axis. Anybody recall how to make the equation for a circle? Yeah?
Is it x squared plus y squared
Yeah, it's x squared plus y squared equals r squared, so I'm going to write that as r squared. R is 2 in this case. Well, maybe I'll just do that. Like, that's the basic format for a circle that's centered at the origin of a particular radius. Now, I would like to, first of all, the radius is 2, right? So in our case, it looks like that. R squared, in our case, it would be 4 because r is 2. And we have to write it as a function, y equals whatever, right? Because otherwise there's no way to plug it into our integration formula. So we are going to solve for y here. That involves first write it this way, y squared equals 4 minus x squared, and then take the square root. And actually, because we use the square root without like a plus or minus, really this does give us just the top half of the circle, which is what we wanted anyway. All right, so this is our function, f of x. And now I think we have all the ingredients to just plug stuff in and work it out. All right, let's see how it goes. So I'm gonna say volume is, I got the pi, and then the boundaries, you can see on the picture, the range of x values that make up this volume goes from -2 to 2. So that's going to be my a and the b. And then on the inside, remember the formula, it says f of x, the whole thing squared. So in this case, it will be root 4 minus x squared dx. All right. This is the volume formula using that half circle there. All right, and let's see if we can work this out. Remember, we said before, up in the box there, the answer should be 32 over 3 times pi. Let's see if we can make it happen. So, any suggestion? What can we do to simplify on the inside? The inside actually looks fairly crazy with the radical sign and then the squaring. What happens with all that stuff? Yeah?
Would you cancel the radical?
Yeah, right. The square root sign just gets canceled by the squaring because those are like inverse operations to one another. So this is just pi minus 2 to 2 and then 4 minus x squared. And that is an easy thing to just do the integral of. This is just a polynomial. So we get pi, and then the integral is 4x minus 1/3 x cubed. And I have to plug in -2 and 2. All right, that's the integral. And now we just plug this stuff in. So we got pi 4 times 2 minus 1/3 times 2 cubed, and then subtract pi 4 times -2 minus 1/3 -2 cubed. Like that. And then, ordinarily I might just leave my answer like that, but I want to check with the little thing that we said before. We should get 32 over 3 pi. Can we try to make that happen? So this, if we just multiply these numbers, of course we have pi on the front of everything, but it's 8 minus 1/3 times 2 cubed. 2 cubed is 8, so this is 8 minus 8/3. And then subtracting pi, and here it's going to say -8 plus 8/3. It's the same, but the signs are all reversed. And I happen to know 8 minus 8/3 is the same as 16/3. I worked this out. 8 in terms of thirds, 8 is 24/3, minus 8/3 is 16/3. Anyway, this is pi times 16/3, and then it says minus pi times -16/3. I'm just simplifying here. Anyway, those two minus signs cancel, and I get pi times 16/3 plus pi times 16/3, and it adds up. Pi times 32/3. That's what we wanted, right? So it really does work out. I find this somewhat satisfying that you can actually work out this volume using the integration formula. And in fact, from a certain point of view, like this formula, v equals 4/3 pi r cubed, I don't know if you ever wondered, like, where does that formula really come from? Well, one place that it can come from, if you want to do things in this way, you can actually sort of come up with this formula yourself using the integration formula from this, starting from here, because this formula basically says integral of r squared, and that's why this ends up with a r cubed over 3, because you're doing the integral of like a r squared. It's a little weird with the exactly where the 4 comes from. It's because of some business in there when you do the integral. We don't need to go through all the details, but that's how you could come up with some formulas like this. All right, great. I got one more, and then I have one for you all. No, I don't. Sorry, I'm mixed up with my papers. Let's talk about a slight variation on this. So actually, all of these ones that we've done so far are easy ones because they are revolved around the x-axis. So I would like to talk about, and these ones are a little trickier. How about I'm sorry, I'm not doing that variation. Sorry, I'm still confused about what I wanted to do and in what order. I want to do 2 variations, and then we'll talk about what if it's rotated around some other axis. Sorry. So one variation is, I'll call this maybe an easy variation. How about rotating around the y-axis instead of the x-axis? I'm not sure how easy this is per se, but it's just like in the stuff that we were doing last time, the area between curves. Sometimes you have to kind of do things sideways rather than the normal way around. And it's similar in this kind of a thing. So when we are rotating around the y-axis instead of the x-axis, you basically do everything the same. So you do everything as x in terms of y. And then you set up the integral. The formula will be the same, but it's like f of y squared dy, right? This is the idea. If you are rotating around the y-axis instead of the x-axis, everything's the same, but you have to rephrase all of your functions and everything else in terms of y values rather than x values. All right, let's just try one example like that. How about, I am again going to take a parabola here, but rotate it around the y-axis instead of the x-axis. So here's the parabola that I start with. This is y equals x squared. But I would like to rotate it this way, so like that. And let's say go up to y equals 1, starting from the origin. So this is kind of a 3-dimensional parabola type shape. There's actually a name for this shape. This is called a paraboloid. It is a 3-dimensional sort of bowl type shape that has the shape of a parabola, but it's in 3D. All right, that is a paraboloid. Can we find the volume of that? So it is, the only difference is it's rotated around the y-axis, which means really we need to, first of all, the a and the b are going to refer to y values, not x values, but they are 0 and 1. I told you the y values. So that's what we're going to use for the a and the b. The thing we have to do, I guess, a little bit of work on is this, f of y. So the function as I gave it to you is written as y in terms of x, but we need to solve it the other way around in order to do our integration in terms of y. So this we are going to solve for x, so that I can write it as x equals some function of y. What do you get when you solve that for x? This is a fairly simple one. What do you say? Yeah.
Root y.
Yeah, square root of y. By solving for x, you would take the square root on both sides. So it is x equals the square root of y. Often when you're solving things by taking square roots, you have to worry about introducing plus or minus, things like that. In these types of examples, it never matters, and the reason is because, so root y, x equal root y, technically speaking, only gives you the part on the right-hand side, but that's good enough for our purposes anyway, because we're going to spin it around the y-axis all the way around anyway. So that the plus minus business you don't have to worry about in this type of problem. All right, anyway, we can just figure all this business out then. So the volume is pi. I go 0 to 1. That refers to these y values here, 0 and 1. And then the formula says my function, which is root y squared dy. And this one works out very nicely. Again, the root cancels with the squared, so all this it says is integral from 0 to 1 of y dy. That, of course, is 1/2 y squared, plugging in 0 and 1. I plug in 1, I get 1/2 times 1 squared, and then minus pi, 1/2 times 0 squared. So this is just power over 2. All right. So this is what I called the easy variation. Easy variation. When it rotates around the y-axis instead of the x-axis, you just have to sort of, sometimes this is a little tricky to do, but you have to solve your function for x in terms of y, and also figure out where your boundaries are in terms of y, not x. But it's not so tricky. There is a more interesting variation, which we should talk about at more length. So, more interesting variation, and this can be harder to deal with, and that is, I will say, shapes where the area is between two curves. And this is referred to as volumes with washers, or the washers method, or something like that. And this you'll see, like if you look at our big checklist of topics, this I believe is number 4 on the list, washers. Actually, everything that we've been talking about so far, people refer to as volumes using washers. It's just that all the examples we've done so far have been easy ones. This is a more complicated variation. Why is it called washers? Here's what I'm talking about. What I mean is something like, if I start with, I said shapes where the area is between two curves. So here is a fairly easy one, I guess, of this type. Let's look at y equals 2x and y equals x. Those are just two lines. And I want to go from, just to keep it simple, from 0 across to 1. And take the region between these two curves, this kind of triangle here, and rotate that shape around the x-axis. So what you get is, something like this also down here. And it's spun around. So this is like, I suppose you could say some kind of cone, but it's like a cone with some thickness to it. Or it comes to a point at the left side there, but the sort of the walls of the cone have some thickness to them. And I'm looking for the volume, just like the solid part of the walls of this cone, all right? This is a slightly more complicated situation, all right? So why is this called volumes with washers? It's because, again, so you cannot just use our basic formula here, like volume equals, pi times the integral of f of x squared, because we don't just have one function, f of x. We have actually two different functions, and we have to decide how to handle those two different functions. Now, why is it called the washers? It's because, again, you want to imagine slicing this shape up into a bunch of little slices. In this case, each slice looks like, let's sort of take a slice right there. It looks like sorry, my picture is a little crowded at this point. Each slice looks sort of like one of these discs, but actually it's more like a ring with a hole in the through the center, right? if you slice this shape vertically on this picture, what you get is sort of a round thing, but it's only like sort of an outer wall which has a gap in the middle, all right? And of course it has a little bit of a thickness, just like our sort of disc type shapes that you get from slicing. So anyway, what is this shape? So each slice is what they call a washer. This is washer as in like a thing that you put screws through. It has sort of, it's the same kind of a disc-like shape with some little thickness, you know, this little thickness of delta X, but it has a hole drilled through the middle. That's the difference between this and the previous type. I guess it has a little thickness there. Ah, it looks pretty good, right? It's a washer, all right? And so, when we do the integral, this time, rather than adding up a bunch of cylinder volumes, we are adding a bunch of washer volumes. And anybody happen to know the formula for the volume of a washer? This is not the kind of thing that you learn in school. Everybody knows the volume for a cylinder, but it's not so hard. Actually, this washer, what is its volume? You could consider just the volume of everything. Like if I imagine filling in the hole, it's the volume of everything, but then I subtract out the volume of the hole. Is that what you were gonna say? Sorry, I didn't see the hand. Yeah, you could take the volume of this thing by just imagining the volume of the whole thing, which is the same as what we had said before, and then you subtract out the volume of the whole. Now, how specifically we're gonna write that is not so difficult. This, of course, has a center, and it has what I'm gonna call an inner radius and an outer radius, right? The outer radius is the one going, you know, all the way to the outside, and then the hole through the middle also has its own radius. So I'm going to call these, this is the inner radius and the outer radius. And the volume of the whole thing would be pi r squared times the thickness, where r is the outer radius. But then I want to subtract off the volume of the inner radius, which would be pi r squared times the thickness, where the one I'm subtracting is the inner radius from the one with the outer radius. Anyway, what this ends up being is basically the volume here will be pi times outer squared times the thickness minus pi times the inner squared times the thickness, right? I am taking the volume of the whole thing and then subtracting away the volume of the whole. Sorry, this is meant to sort of appear on one line. I just ran out of space. I fix it up a little, like this, right? Of course, you could factor the pi out of all of that stuff, and then write down the volume formula as an integral. And here is our formula. I'm going to put A and B as usual. And basically it's outer squared minus inner squared dx. It comes from what I wrote there in red if you just factor the pi out of everything and then turn those delta x's into integrals with a dx. And this is the formula for volumes using washers. And this business about the outer and the inner can be a little confusing sometimes, so we're going to do a bunch of examples like this. All right. Any thoughts so far? I mean, we can just try. How about let's just try this one that I started drawing the picture of, right? The inner and the outer, of course, each of these will be two different functions, right? And in that example from here, I just straight up told you what those two functions are. So this one is a fairly easy to tell sort of what's the outer and what's the inner. This is a big question or a big problem. In this example, it's pretty easy, but in other ones you will see. Sometimes it's difficult to figure out what should I be using for the outer and the inner. So anyway, let's I'm just going to copy this picture down there. So this one here, we don't need to see that anymore. So here it's going to say volume is pi. Okay, what are the a and the b? That's just, as usual, the range of x values that I'm considering, and I put it on the picture, is 0 to 1. And then it should say the outer radius minus the inner radius. And the way that I think of this on a picture like this, maybe I'll take away this scribbly stuff so you can see more clearly what I'm saying. The way that I would think of this is look at sort of here, that's the outer, and something like here, that's the inner, right? The outer radius is the one sort of all the way up to the outer edge of this shape, and then the inner radius is the one that determines the kind of hole in the middle. And each of those should be a formula, and you can, in this example, it's fairly easy to say. The outer is 2x, so I go 2x squared, and then minus just plain x squared. Remember, you always have to square these things. That's part of how the formula works. Right. Now that it's set up, it's fairly straightforward to do the integral. So let's just finish it off. So it's a pi here, integral 0 to 1. Simplify on the inside before doing the integral. What do we get from 2x squared? Somebody want to shout it out? 2x, the whole thing squared. What do you say? 2x squared? You got to do something with the parentheses and the... Yeah, you have to square the 2 and also square the x. So it should be 4 times x squared. And then minus x squared is just x squared, right? Before integrating, I would just subtract those. It's pi integral 3x squared, right? 4x squared minus x squared is 3x squared. And then we can do the integral. It's pi stays out front. 3x squared becomes, I guess, just x cubed, right? 3 times 1/3 x cubed. Plugging in 0 and 1, this is pi times 1 cubed minus pi times 0 cubed, which is just pi. Somewhat strange answer, since it was such a weird shape that we started with, but its volume is just pi. All right. Any thoughts? I got one for you all to try, and then we'll try some more variations. So that was a fairly easy one of this washer thing, and this next one also is fairly straightforward, but I just want to make sure everybody is getting it so far, and then we'll try and get a little fancier as we go. How about this is, I'm going to go over to, again, 0 to 1. Let's say this is y equals x, and this is the parabola, y equals x squared. And I want this region being revolved around the x-axis. So it's sort of like, it's a similar kind of sort of cone-like shape, similar to before, but it has a different, I suppose, a different shape to it. It's curvy on the inside. See what you think. x4 came from 2 squared times x squared. Like when you square the square. But here there's no other thing.
Yeah.
Sorry. Okay. Here now? I'm good here? Yes, I think so. Yeah, that's great. So this step. We have to go everywhere. Except for the place here. Great. Excellent. Yes. This looks good. There's 2 columns here. Okay. How you simplify it? When you go x to the 4 minus x squared,
I just keep going.
do that. I think you're thinking of something like 4x minus 2x, so you subtract that 2x. But since their powers are x, so scribble this out and then just go directly from here to something like that. But it's so that gives you that, but this one gives you another one. Okay.
Yeah.
All right, people did pretty good with this one. I'm just gonna write down what I think it says. The setup is like this. The outer in this case is x and the inner is x squared. And so because of the squarings in my original formula, I need to say x squared and then minus x squared squared. Try to simplify this. It just looks like x squared minus x to the 4 because x squared squared is x to the 4. But you can't simplify any more than that. You have to just leave these as 2 separate things and then do the integral. So it's going to say 1/3 x cubed minus 1/5 x to the 5. And I plug in 0 and 1. So it's pi times 1/3 1 cubed minus 1/5 1 to the 5 minus, same thing with zeros, 1/3 0 cubed minus 1/5 0 to the 5. And most of that can sort of simplify away. This is all zeros over here, and the first part that you can ignore those ones if you like. 1/3 minus 1/5, whatever that is, times pi. This is my answer. It looked like most people got something like that. Great job, if you did. All right, great. Now I am ready to talk about rotating around a different axis, and that's what is slightly more difficult, and that's when it becomes a little tricky to figure out the inner versus the outer. I think in this example it's pretty clear what the inner and the outer is. The outer is, you look at sort of these distances from the middle and all the way to the outside, and the outer one is x and the inner one is x squared. Fairly straightforward. What about rotating around a different axis? And this is where things get, in my opinion, a little confusing. These previous ones I feel like were not so confusing. Rotating around a different axis. All right, here's what I mean. I'm going to have an example like, let's take this parabola, but going down. So this is y equals negative x squared, just to mix it up a little. I use x squared too often. And something else to mix it up a little, I'm going to take the region between x equals 1 and 2 instead of going 0 to 1 every time. All right, so this, all right. And as my final thing to mix it up a little, and this is really where the interesting bit comes in, I want to rotate it around this line at y equals 1 instead of the x-axis, all right? So if you saw this problem, say on a homework assignment, this would often be described in words, although sometimes they'll show you the picture, but this would be something like, find the volume of the region bounded between x equal 1, x equal 2, the x-axis, and this function, y equals minus x squared. So this is, in words, how I would describe this shaded region here. It's between x equal 1 and x equal 2, and the x-axis, and y equals negative x squared. And I want to revolve around the line y equals 1. That's this sort of dotted line that I wrote here. All right? So the shape that I'm talking about, this sort of 3D shape, consists of that sort of region down there, but it's being revolved up here, sort of like up into space. Its mirror image has this kind of shape, right? And it looks like that. This is kind of like a Christmas tree holder kind of a thing. It's a round thing with a hole in it. I actually made something that shape recently, like a few days ago. I had well, you already know, I got a new shirt for Christmas. I also got a new toothbrush, a new fancy electric toothbrush. And I made myself, I have a 3D printer, and I made myself a little, like, thing to hold it in. I had an old toothbrush that broke, and I never really liked it. So I said to my wife, I want a really nice one this time. And I got a nice one, but it didn't come with like a little stand. So I made a little stand, and it has this shape to it. It has a sort of swoopy thing around the edge, and it's round. That's what this shape is. All right, aren't you glad I told you that little story? It just makes it so much easier to understand. How do we find this volume? All right, this is what we have to think about. We are going to use the same formula. It is a matter of figuring out what is the inner and the outer, and it's not so easy in this example. So we are still going to do this, pi, the integral, it's outer squared minus inner squared, right? Actually, it is still easy to say, what are the a and the b? What's the numbers for the integral sign? What do you say? That is the range of x values. Yeah? 1 and 2. Yeah, you can tell on the picture. I said to go from 1 to 2. All right. The big sort of hard part about this is, what are the inner and the outer? What are the outer and the inner? That's the real question here. That is more difficult in this example than in the other. So I am going to, just to help out, maybe I'm going to write a less crowded version of that picture. We have our axis of rotation up here, and then the shape is that, right? I'm not going to shade it in just because that is makes things a little bit confusing. The line on the bottom, remember, was y equals minus x squared, right? Minus x squared. So on this picture, it seems to me the outer and the inner are represented by sort of that distance is the inner from here to here, right? And the outer is from here all the way out to there, right? That's the inner and the outer. picture here. And then can we just say what they are? The inner, in this example, I think the inner is it's fairly simple if you can visualize it correctly. Can anybody say what's that inner radius? I'm talking about the distance of that shorter line there. You could actually show me on the fingers. I see this. The answer is 1. Yeah, that distance, that inner radius, no matter where you go, sort of from left to right here, that's always the same, and this distance here is always 1, right? So one way that you could think this through, if you really want to be fancy about it, this rotation axis, of course, is up at y equals 1, just because I told you. And that distance right here goes from, so this one right here, this is the inner, and it equals 1, right? The way to find the length of this is just a straight segment which starts at 1 at the top and goes down to 0. And so its height you can find as the sort of the number at the top minus the number at the bottom. In this case is 1 and 0, so it's just 1 is the inner radius. What about the outer? Now the outer radius actually does change as you move from left to right on this shape, right? It changes according to this curve. But unfortunately, the outer is not just equal to that, because the distance of the outer radius is measured from here all the way down, not from the x-axis all the way down. And so we have to be a little cute about finding the outer radius. So the outer is, you know, if I were to just draw this one more time, the outer is this distance here, right? And the way that I would find this distance, I would suggest this vertical distance would be the value at the top minus the bottom. Top minus the bottom y values. The y value at the top is 1. The y value at the bottom is y equals negative x squared. And so this is 1 minus negative x squared, also known as 1 plus x squared. This, in my opinion, is a little tricky, because this 1 plus x squared is the outer radius, which actually looks quite different from the function is negative x squared. You have to be very careful about starting with a function and changing it into this format. The outer radius in this case is 1 plus x squared. All right? So let's see if we can do this integral. And then I have really, as usual, the integral is not so hard to do. It's figuring the setup is more difficult. But anyway, we have the inner here is just 1. The outer is that. So when I draw the integral, or when I set it up, it is the integral from 0 to 1, it's 1 to 2, right? And then the outer squared would be this, minus the inner squared would be that. I'm plugging in the outer and the inner, and you got to square each of them. The outer squared minus the inner squared. All right, let's see if we can do this integral. It is a little complicated on the inside there. Of course, 1 squared is 1, so that's no problem to deal with that. Anybody want to suggest, how do I simplify this thing? 1 plus x squared, the whole thing squared. Is it the same as 1 squared plus x squared squared? I just square each of those two things. Actually, it is not the same as that. You got to do the FOIL thing. Remember, when you have a thing like this and you're squaring it, you have to multiply this out. So this, you could do this maybe on the side if you like. This is 1 plus x squared times 1 plus x squared, right? And you got to do the FOIL. When you do the FOIL, you get 1 on the front, and then on the inside it's x squared, and on the outside it's also x squared, and on the end it's x to the 4. So this, when I square it out, is 1 plus 2x squared plus x to the 4. That's the FOIL thing. And then I go minus 1. That was from the inner part. And then this is now looking fairly straightforward. It's just a polynomial. We can simplify very slightly by just canceling the ones, right? I have a 1 here and a -1 here, so those can go away. But otherwise, we can just do the integral directly now. So it's pi, sorry, I'm doing the integral in this step. So it's going to be 2 times 1/3 x cubed plus 1/5 x to the 5. And plug in 1 and 2. And that's 2, can I write 2/3 there? 2/3 times 2 cubed plus 1/5 times 2 to the 5th minus, same business with ones, 2/3 times 1 cubed plus 1/5 times 1 to the 5th. All right, that's the answer. Anyway, what's important about this example though is just being able to figure out the inners and the outers. That's the hard step in this example, in my opinion, or it's certainly what makes this one harder than the previous ones that we've done. Finding the inners and the outers. All right, can we try another one like this? And then I have several for you to try. Let's just focus on the part about finding the inners and the outers, because I think that's the hard step. Doing the integral is usually just, I mean, we all know how to do the integral. That's fairly routine at the end, but finding the inners and the outers is the hard part when you're doing this washers thing. Finding inners and outers. Let's try something. How about x squared here? But I'm going to rotate around y equals -3. All right. So it's this shape, and let's just go over to 1. That region being rotated around like this, so it becomes something like that down there. All right. Let's just set up the integral, and then we don't need to actually do the whole thing, but just the setup, which is the harder step in this problem. You might want to, it's probably better if you don't shade this in just for the sake of drawing. I like to sort of draw a little line. This is the inner, and this is the outer, right? These are the lines going from the axis, the rotation axis, up to where the shape starts, which in this case is just the x-axis. And then also the line that goes from the rotation axis all the way up to the outer boundary of the shape. All right. And these two lines, we can find their heights by, like I said before, doing sort of the top of it minus the bottom of it. Or sometimes you can just kind of common sense them out. But can we, let's talk about the outer here. I typically am going to think of this as the top of the line, the y value at the top minus the y value at the bottom. So I'm going to think of it as the top minus the bottom. Where in this case, can anyone say what the top and the bottom are of? I'm talking about this segment right here. Yeah?
The top's x squared and the bottom's -3.
Yeah, the top is x squared, the bottom is -3. Excellent. So it's going to say x squared minus -3, which is x squared plus 3. So that's the outer in this case. Great. And then the inner, this one you can kind of sort of common sense your way through it. Although you could, if you like, still think of it, if you want, in terms of this top minus the bottom thing. Of the inner line, that's the line on the left, this one right here. The top is at 0, y equals 0, and the bottom is at y equals -3, which is 0 minus -3, which is 3. I said you could also just kind of by common sense, that distance is 3, right? From the x-axis down to -3, it's 3. But if you want to work it out in full detail, this is what it would look like, and you get 3. All right, excellent. So the setup here, I'm not going to do the integral like I said, but it's going to be pi 0 to 1, and then outer squared would be x squared plus 3 squared minus inner squared, like that. And if you really wanted to calculate this, you would have to do the FOIL on the first part. But I don't think we need to go through it. All right. Any questions about that? I have several of these for you to try. And your job, so I'm going to give you four. Yeah, 4 of them. Your job is just to set it up. You don't have to do the whole integral. But let's see if you can do just set up the integral. How about this one is very similar to the one we just did. So it's this region here, rotated around -2. And this goes from 0 to 2. Right? That's one. I drew 4 of them. See what you think. I hope you can understand my pictures. Let me know if not. last one I didn't label. The y value there is meant to be 1. Maybe you guessed. I like 1s and 0s. Kind of guy. Everything okay?
Would you like his friends in here?
Yeah, but that's cool.
This distance from there to there should have any distance. It's just straight line.
Gotcha.
How's it going here? Very well. Yeah, so this, as far as that number line, that's the outer core. Okay. Like this is okay. Okay. Okay, yeah. I would suggest I would draw these segments down here so that I can say it's like this one, there to there, yeah, top. That's the inner. Okay. Doing okay?
I'm trouble with us.
Okay. So you said the inner is the outer. Yeah, okay, that fits now. The two segments you should be looking at is like that distance is the inner, and then that distance all the way to the top is the outer. Okay. That's helpful. Like so for the outer, for instance, it's from there over to that line. And I was thinking like y at the top minus y at the bottom. What would that look like?
So that's 1. So it'd be 1 minus
Two, right? Okay. Yeah, and actually, it's not so hard to decide. Like the distance from this down to there is always going to be 2 because it's 1. And then the other distance would be from the curve down to.
Oh, I was thinking of starting at 0.
What's E on the interval
Yeah, I guess I didn't tell you that, but you can figure that out because of where the y value is 1. You can tell where the x value ought to be. All right, can we talk about these? I know I said I was gonna finish a few minutes early, so. These, I hope you agree with me, are a little tricky. So if they seem confusing to you, then you are not alone. I am here for you. I'm just gonna separate these out a little bit. So as I was walking around, pretty much everybody, whoa. I don't know what happened. I dragged up too much. Okay, the first one here, we said as I was going around, pretty much everybody worked this out well. Of those two lines, the shorter little segment there is the inner. In this case, you can just tell by looking at that, the short segment there always has distance 2. It's going from the x-axis down to -2. But if you like, in terms of sort of top minus the bottom, which is how I like to think this through, it's 0 minus -2, which is 2. And then the outer is the distance from the curve down to the rotation axis. The curve is x cubed minus the rotation axis is -2. So this is x cubed plus 2. So the volume in this case would be pi integral 0 to 2 x cubed plus 2 squared minus 2 squared, like that. I think everybody got this one as I was going around. Any questions about that? Great, let's try. The other ones are a little more interesting maybe. So this one here, I'll just move it around. This time, the inners and the outers that you're looking for would be like that. That distance is the inner, and this distance is the outer, right? The inner, this first one is the inner because it's the shorter of the two distances, and it's the distance across the hole in the middle, as opposed to the other one is distance all the way out to the outer edge. Anyway, the in this case, the inner would be that the segment that I drew on the left, the shorter of those two. As usual, I'm going to think in terms of top minus the bottom. The top here, the y value is 3, and then subtracting the y value. The bottom is just the curve, which is x squared. So this is 3 minus x squared. That's the inner radius, and the outer is the other one over there, the top being 3, the bottom being 0, the x-axis, so that's just 3. So this one, the volume is integral pi, integral 0 to 1. Outer squared would be 3 squared minus inner squared, 3 minus x squared squared. Any thoughts about that one? I hope you got something like that. Great. Okay, this next one. So this time, my segments that I would draw, that's the inner, that's the outer, right? It is kind of the same thing every time, but I find it very easy to get confused, even if I'm doing something that looks the same from one example to the next. I find it easy to mess these up. Anyway, in this case, the inner, what do you think? Somebody work this out? What'd you say? Yeah? 2, yeah. If I was doing sort of tops minus the bottoms, I'm looking at this segment on the left here as the inner one. It would be the top is 1 minus the bottom is negative 1, which, like she said, is 2. And then the outer, what'd you say for the outer? X squared plus 1, you said? Yeah. X squared minus negative 1 is how, if you were writing it sort of in steps. This longer segment here, the top is at x squared, the bottom is at negative 1. So I would write it this way, which is, as she said, x squared plus 1. Great. So this one, the integral would be pi integral, this time it's 1 to 2, which doesn't really matter for the rest of it. And then outer squared minus inner squared, like so. Yeah, excellent. All right, and finally, this one. This time, my inner and outer segments look like sort of, here's the inner, here's the outer, like so. And then, somebody else want to tell me what'd you get for the inner on this one? Yeah? Root x plus 1. Yeah, great. The top here is on the curve, which is root x, and then I go down to the bottom is at negative 1. So I would write this in steps as like this, right? Which is root x plus 1. Excellent. And then the outer goes all the way. The top is 1, the bottom is negative 1. So the outer in this case is 1 minus negative 1. That's the top and the bottom, which is 2. And so the integral this time would be pi. Actually, I didn't tell you the x value right there. It goes from 0 over to this value, but you can tell because the square root of this has to be 1, that also has to be 1. So this is 0 to 1. And then outer squared minus the inner squared. There you go. All right, that'll do for today. Please check out the homework. Let me know if you, try and do them tonight. If you have questions, I'd be happy to chat, right before class or right after class or whatever tomorrow. And please do let me know if you have problems with the grades.